What's up, future billionaires and tech enthusiasts? Welcome back to the channel where we decode the nerdy stuff so you can sound smart at parties and, maybe make a few bucks along the way. Today, we're diving deep into something that Wall Street is totally missing. Something so under the radar it's practically wearing a stealth bomber outfit. While everyone's busy freaking out about OpenAI's gazillion-dollar deals and Trump's latest trade tweets, NVIDIA just dropped a chip that's about to turn the entire AI market on its head. And guess what? You're going to be the first to know all about it. I'm talking about NVIDIA's new Reuben CPX GPU, and trust me, it's not a sandwich, though it is deliciously innovative. This bad boy is going to fundamentally change how AI data centers work, and I'm going to spill the beans on which stocks are about to moon because of it. Your time is valuable, so let's get right into the silicon-y goodness. All right, first things first, because I'm not here to hold you hostage with suspense. Here's our roadmap for this epic journey into the future of AI. 1. NVIDIA's insane new Reuben CPX GPU. We'll break down what this chip is, its purpose, design, and performance. 2. AI, our infrastructure revolution. How this chip will fundamentally change everything we thought we knew about AI. 3. Stocks I'm buying. The juicy part. Which companies are about to ride this wave to the moon? There's a ton to talk about, so let's dive right into the chip itself. A few weeks ago at the AI Info Summit, NVIDIA, in their usual ninja-like fashion, announced a GPU called the Reuben CPX. Now, before you think it's just another graphics card for gaming, though it would probably run Crysis on Ultra ×10, this is a new kind of GPU specifically focused on accelerating massive context inference. Massive context inference? Sounds like something a supervillain would say, right? But fear not, my friends. I'm here to translate. To really get this, we need to understand the three main phases of generative AI today: training, post-training, and inference. Think of it like raising a super-intelligent robot butler. Phase 1. Training. This is where our robot butler, let's call him Jeeves, goes to robot college. He learns everything: structures, patterns, relationships from massive amounts of data. Imagine Jeeves reading every book ever written, watching every YouTube video, and probably even scrolling through your questionable TikTok history. Today's top-tier models like OpenAI's GPT-5, Google's Gemini, or Anthropic's Claude are trained on basically the entire open internet. It's like trying to fit all the knowledge of humanity into a giant digital brain, using tens of thousands of GPUs working together like a synchronized robot army, all connected by super specialized networking equipment. It's a massive undertaking. Phase 2. Post-training. This is where Jeeves gets his manners. He's aligned and fine-tuned for specific tasks. We teach him things like, don't recommend political content if someone just wants a movie, even if you have opinions on the latest election. This is also where guardrails get implemented, not just to stop biased or unsafe outputs, but to keep the AI on task so it doesn't waste precious tokens on stuff that won't make money. For example, imagine if Netflix or Apple TV had an AI agent that curated content for you. If you asked it a question about politics or religion, it shouldn't respond with a political or religious answer. Not just because you might disagree with the response, and trust me, people disagree a lot, but because that response costs tokens to generate, and it doesn't get you to engage with the content. Post-training is less compute-intensive than training, but it still takes some specialized hardware and software to turn data labels and human feedback into updated weights for our super-smart robot butler. Phase 3. Inference. This is where Jeeves actually does his job. A user gives him a prompt, and he generates a response, like answering a question, generating a video, or compiling code. He does it one token at a time, like a master chef adding ingredients. But here's the kicker. While training needs a ton of raw compute power, inference needs low latency and lower costs per token. Think of it this way. Training is all about building the best AI model, the best chef. Inference is all about having the network speed to serve the most users or prompts per second, the fastest, most efficient restaurant. That's why hyperscalers like Amazon, Google, Microsoft, and Meta platforms all have their own custom chips for inference, while they use NVIDIA's much more powerful but also much more expensive GPUs for model training. They're not competing, they're doing fundamentally different things. It's like using a bulldozer to build the foundation of a skyscraper, and then a precise crane to put the finishing touches on the penthouse. This is also why OpenAI signed multiple $100 billion deals, not just with NVIDIA, but also with AMD, to use their GPUs for inference, and with Broadcom to build their own custom inference chips. And this, my friends, is where NVIDIA's new Reuben CPX GPU swoops in like a superhero in a silicon cape. It turns out that inference itself is broken down into two very different steps: prefill and decode. The prefill phase is like Jeeves quickly scanning an entire book you handed him. It takes your entire input prompt, converts it into tokens, runs them through the model, computes the results for every token, called key-value pairs, and stores those key-value pairs in the chip's memory. Today, input prompts can be millions of tokens long. People are attaching multiple PDFs, videos, or even entire code bases to their prompts. Imagine dropping every Harry Potter book and every Lord of the Rings book into Google Gemini 1.5 Pro's context window, for science. NVIDIA's Reuben CPX chip is designed precisely for this kind of massive context inference. It has a ton of compute power to process millions of tokens in parallel, but it uses lower cost, lower bandwidth memory, because that's not as crucial for this initial scanning part. Think of it as a super-fast librarian who can skim thousands of books in seconds, but doesn't need to remember every single word with perfect recall immediately. The second phase of inference is called decode. This is where our robot butler Jeeves actually starts talking back to you. The chip retrieves all those key-value pairs it just generated, calculates the next token and its key-value pair, adds that to the sequence, and then repeats this process until it finishes generating the entire answer. It's like Jeeves actually reading aloud the answer from the books he just skimmed one word at a time. But here's the crucial distinction. While the prefill step takes a ton of compute power to calculate those key-value pairs for millions of input tokens, this decode step needs a lot more memory to read them all in. But it needs a lot less compute to generate the next token, one token at a time. So just like training and inference need totally different kinds of chips, so do the two parts of inference itself. This fundamentally changes how every company will invest in their AI infrastructure going forward. This is why I think NVIDIA's Reuben CPX GPU is such a massive deal. This is why it's so important to understand the science behind the stocks. And this is why one of the best investments you can make to get ahead is understanding AI. So the two phases of inference have very different hardware requirements. Prefill takes a ton of compute, but can get away with much slower memory, while decode takes tons of memory bandwidth, but nowhere near as much compute. And the difference in prefill inference performance between NVIDIA's Reuben CPX GPU and the standard Reuben GPU? It's going to be massive. We're talking up to 4 times the compute per dollar. Less than half the memory costs, since it doesn't need specialized high-bandwidth memory. 3 times the throughput per GPU. And up to 90 cents per GPU saved every single hour, depending on electricity prices, which, by the way, is one of the biggest costs of operating a data center. Imagine the savings. As a result, the NVIDIA Reuben CPX could provide 30 to 50 times the return on investment for prefill inference over the standard Reuben 200 GPU. That's a huge deal because inference accounts for a whopping 80 to 90% of the total costs for a given model. Training only happens a handful of times, while inference happens at huge scales around the clock across millions of users and applications. It's like building one really expensive rocket ship, but then flying it 1,000,000 times a day. Now, here's the part that will put you ahead of every Wall Street analyst covering AI infrastructure. It's not just about this one GPU. The global AI data center market is currently expected to roughly 9x in size over the next 9 years, which would be a 27% compound annual growth rate through 2034. That's already over twice as fast as the growth of the S&P 500. But I spent all this time walking through the requirements for every phase of generative AI, not just inference, but training and fine-tuning. Because I now believe we'll see more specialized chips for those phases too. For example, since NVIDIA made this chip for the prefill inference step, they'll probably also make one for the decode step next. Or they could make another chip optimized for reinforcement learning and tuning models based on feedback that runs continuously, which will blur the lines between training and inference altogether. Imagine a chip that's constantly learning and adapting. First up, the undisputed king, the one foundry to rule them all, Taiwan Semiconductor Manufacturing Company, TSM. Ticker symbol, TSM. This is the only foundry on Earth advanced enough to make chips for NVIDIA, AMD, Broadcom, Apple, and all the custom AI chips for hyperscalers like Google, Amazon, Microsoft, and Meta platforms. As demand for inference grows, demand for chips to power it grows even faster, since data center infrastructure is planned out years in advance. So, as TSMC's customers start creating more specialized chips for the different phases of AI we just discussed, like prefill, decode, and fine-tuning, there will be even more chip designs and higher demand for wafers, which, for TSMC, translates to more volume for their most advanced and most profitable nodes. It's like they're selling the shovels in a gold rush, but the shovels are made of pure unobtainium. Next up, the obvious big players, the hyperscalers themselves. Google, Microsoft, and Amazon. Like I said earlier, the NVIDIA Reuben CPX could provide 30 to 50 times the return on investment over the standard Reuben 200 GPU. But the trade-off is that this chip is only for the prefill phase of inference, as opposed to being a general chip that's useful for many kinds of workloads. So the next most obvious bet is on the hyperscalers themselves, Google, Microsoft, and Amazon. These guys have enough total workload demand to deploy, power, and coordinate these specialized chips at massive scales, and then pass the cost savings onto their customers in a way that smaller competitors might not be able to do. Imagine them as the giant supermarkets of AI, able to buy in bulk and pass the savings on. And right behind them are companies like CoreWeave and Nebius, who build and operate high-performance cloud infrastructure optimized for massive language models, generative AI, and deep learning. These companies deploy the latest GPU and accelerator hardware, which will include any phase-optimized chips to give their customers the kinds of speed, scalability, and cost efficiency they couldn't get if they built their own AI infrastructure. Between the two, I personally prefer CoreWeave because they're NVIDIA's biggest public investment, representing around 90% of the company's stock portfolio. When NVIDIA puts its money where its mouth is, you listen. Then there are the companies that connect all these amazing chips together, like Arista Networks, ANET. Arista designs specialized switches, network control software, and management tools to build huge, reliable, and fast networks at large scales. Think of them as the super-fast highway builders for all this digital traffic. Arista Networks also works closely with Broadcom, AVGO, who just partnered with OpenAI to build their custom inference chips. Arista's switches and software are actually built around Broadcom's ultra-fast Tomahawk switch chips, which is how they're able to stay ahead of the growing networking needs for AI today. So, as new kinds of phase-optimized chips enter the AI market, companies like Broadcom and Arista Networks will be the ones connecting them together to handle highly parallel workloads at incredibly high speeds. They're the glue that holds the AI world together. Hopefully this video helped you understand NVIDIA's insane new Reuben CPX GPU, how it will fundamentally change AI infrastructure as we know it. and the kinds of stocks that will win big as a result. Because understanding a company's products and not just their profits is a great way to get rich without getting lucky. Thanks for watching, and until next time, this is Wealth Investopia, reminding you that the best investment you can make is in you.